That okay?
So yeah, but maybe I'll introduce the speaker. So today we're very happy to have Wei Bu from Edinburgh, and he's going to tell us about a systematic approach to celestial holography. So let's welcome our speaker. Okay,
Thank you, guys.
please share your
Uh,
screen.
I don't hear in class. Yeah, I will. Yeah. So you might.
Okay,
Sorry
there
about
you go. We can see
that.
your screen. Okay.
Yeah. Everybody can see the screen. Yeah.
Yes, I think so.
Yes.
Yes.
Okay. Cool. So okay, I'm going to talk about some work I did with this guy, Sean Seat. He's a grad student in Cambridge. We wrote 3 papers together the past year or so on the topic of a systematic approach to celestial holography. So this program, I'm going to start with very generally, tell you about what the physics is and what the toolbox we're using is, and then what we actually did. So the program celestial holography refers to it's an effort to reconstruct dynamics and physics in 4D asymptotically flat spacetime, using, if you like to call it, a holographic way of approaching it. So 4-dimensional asymptotically flat spacetimes are these classic spacetimes where the metric looks exactly like Minkowski space at asymptotic infinity. That means it has the same causal structure as Minkowski space itself. So for those of you who don't know, Bondi back in 62, he got this coordinate system working called Bondi coordinate, and what that means is he wrote spacetimes as for example in 4 dimensions, a 2-sphere and some radial direction called r, and then some null direction called u. This is retarded time, and he was saying you can do an asymptotic expansion in the radius r to indicate how far you are from the deep interior, from the origin. And at asymptotic infinity, there's some manifold called scri, which is on the boundary of, say, Minkowski space and any of these 4D asymptotically flat spacetime. So a Penrose diagram, you know what it is? It's when you do a conformal compactification of Minkowski space or any other, or in some cases, other asymptotically flat spacetimes, and it manifests the causal structure. So scri is this thing living it's called null infinities, where massless particles end, trajectories end at the conformal infinity. So its topology is scri is isomorphic to r cross sorry, S2. So this r is the null direction, S2 is the celestial sphere. So in 4 dimensions, of course. So let me break you a piece of history to start with. The study of this reconstruction problem in this class of spacetime, well, you know about the ADS, but in asymptotically flat spacetime, it actually all started in the 60s and 70s. The first thing was the surprising discovery of asymptotic symmetry group. So this means so people were trying to, Bondi and Sachs in particular, they were trying to solve the conformal killing equation, which you know, as you probably know. The killing symmetries are generated by these Poincare generators in Minkowski space, for example. And they were trying to expand the conformal killing equation order by order in the radius direction in R, and trying to solve it at large R on the 1 over R leading 1 over R piece. What that amounts to is they're looking for diffeomorphisms that actually acted on null infinity non-trivially at infinity. So this is an asymptotic symmetry group, if you like. They're looking for the solution of conformal killing equation. And you know, as a physicist, you'd expect to find some version of Poincare group or even a subgroup of Poincare, because you're sort of solving the equation order by order. You should get some sort of sub solution to the full Poincare group. And instead, what people found was this, surprisingly, this infinite dimensional BMS group, which was a semi-direct product between SL2C, so the usual linear conformal group with some null translation direction along this direction, along U, called super translation. So that's the BMS group, very surprisingly. And what they do is the generators actually act on asymptotic components of the metric. These are called asymptotic data. For example, the Bondi mass aspect, you might heard of these words, Bondi mass aspect, the shear, the News tensor, derivatives of the News tensor, and so on and so forth. So, and then Ted Newman, in these papers, he picked this up, this discovery of BMS up, and said, okay, so these BMS group, the asymptotic symmetry groups, they shift these asymptotic data. So can we just, starting from the asymptotic data and the manifold scri, can we reconstruct space-time somehow? Minkowski space itself or other 4D asymptotically flat spacetimes? And the answer for him was partially yes. And the reason it works is because so he was characterizing, let me draw some diagrams. If you start with a point in bulk Minkowski space with coordinate, say, x mu, this is 4dx, the mu goes from 0 to 3, and signature 1, 3. And you consider a null geodesic congruence. What that means is you just imagine yourself standing here and then turning on the light torch. And then the light cone goes out. It cuts, this is scri at a celestial sphere. This is at a very particular value of u. Cuts scri at a particular celestial sphere. This is a topology S2 sphere. And he was saying, okay, let's characterize this cut by writing down some differential equation, a homogeneous differential equation on the sphere. So he wrote down some second order differential equation to characterize the cut. And then when you try to solve it, you get a 4-parameter solution, 4 parameters family of solution. And it turns out that 4 parameters are, the 4 coordinates you started with back in the bulk. So in this way, he was able to reconstruct Minkowski space, for example. But when he was trying to extend this to other 4D asymptotically flat spacetimes, he found out this only actually works for a very special class of spacetimes, which is called a radiative self-dual spacetime.
Oh, sorry.
The self-dual here means...
Can I ask a question?
The Wiles tensor... Yeah.
You said
Sure.
Solving some differential equations. Do you mean solving some geodesics and push it backward? Or?
No, so it's something called the good cut equation. Do I write it down? Yeah. So this is, you can imagine like this. Starting from Minkowski space itself, just don't worry about scri or anything asymptotic. You can characterize a light cone at any shear, basically. And there's an equation for that. And if you push r, so you have some shear, which is a function of r, z, and z bar. Z bar are coordinates on the sphere. It's some second order differential equation. Let's write the homogeneous one. This is the thing in Minkowski space. It's just characterizing the light front of the null geodesic congruence, which is a sphere. And when you push r to infinity, you can expand this function as well. At leading order 1 over r, it looks like this. And of course, the homogeneous differential changes as well. Is that okay? So you can think about it this way: a good cut, a good cut equation geometrically, what it means is it has to be a cut that's coming from a point, null geodesic congruence coming from a point back in spacetime. If it's not from a point, it's not a good cut.
I see. Okay, I see. Thanks. So G is basically describing this cut on the celestial sphere.
G when you solve it is U. It is U. Okay. Because on scri, U is the cut, position of the cut.
I see.
So when you actually solve it, you will find G is X out. Let me write. What's the notation you guys are gonna understand? So if I write outer product for the celestial sphere coordinates is Z alpha, Z bar alpha dot. Okay. Do you guys know the? Let me get into the notations and then tell you about it. Yeah, that's right. This is just motivation part. And Newman found out this reconstruction geometrically actually only works for very specific radiative self-dual spacetime. And Roger Penrose later picked it up and said, well, I can generalize this if you give me more data than the asymptotic data. It generalizes to work for any spacetime with the self-dual Wild tensor, not just radiated ones, but still self-dual. This is some construction called twisted space. It's the toolbox I'm going to use today. But you see, the reconstruction problem in 4D asymptotic flat spacetimes, started in the 60s and 70s. It's not something completely new. People have tried these ideas before, and twisted theory was very much like a big part of the solution back at the time.
Can I ask one more question? When you say you can reconstruct the bulk, you meant, but it has to be pure Minkowski. If it were not, it is asymptotically flat
or
self-dual. Sorry?
Or self-dual.
Or self-dual. So I can depart from Minkowski space. I can have some curvatures in the bulk, but I would still okay. As long as it is asymptotically flat.
So there are two things I require. One is the causal structure infinity, which is asymptotically flat. Two is the Wild tensor of the spacetime is zero. Sorry, it's self-dual. So anti-self-dual part is zero. You only have half the Wild tensor.
Okay, I see.
That's what self-dual means. And then, so today's talk, what we're going to do is use twisted theory, which is a geometrical machinery.
Sorry, just one more question. So, a flat space Wild tensor is just zero, right?
Yes.
And all the conformally flat geometries would also have zero Wild tensor, right?
That's correct.
Okay, but then you would say ADS space, for example, it's would not apply because the asymptotic structure is not correct.
That's right.
Okay, I see. Thanks.
Yeah. Okay, what does this class of spacetime, self-dual spacetime, include? So there are, Minkowski space itself, very importantly, and then these gravitational instantons, if you know what that is. They are defined as, spacetimes with self-dual Wild tensor. And it depends on whether they're Ricci flat or Ricci scalar flat. They can be, the Gibbons-Hawking gravitational instantons or the Brune in conformal gravity. But all of these are examples of self-dual spacetime. And then 3 is very importantly, so all black holes in 2-2 signature are self-dual radiated.
I see.
Cool. So many others, of course.
I see.
There are simpler things in them. Okay, so today's talk, we're just going to use this machinery to do the reconstruction problem in a much more modern language. So I'll break it down for you step by step. We'll see how far we can get. So let's start with I have the word celestial holography in the title. So what is that exactly? So it's a proposal proposed by Straminger and his collaborators in 2017, around that. And it's a proposal to match on-cell data on both sides in Minkowski space and the celestial sphere. So how does this come about? It's all based on this observation of local Lie group isomorphism between 2D conformal group SL2C and 4D Lorentz group. So those of you who know embedding space formalism, this is very simple. Or any of you who know a little bit of group theory, there's a one-to-one map between these two groups, the generators. So then he says, okay, if you take a momentum eigenstate, let's say this guy, omega here is some massless particle. Omega is some energy scale. So I'm writing my momenta k mu is a null momenta, so k squares to 0. And the scale of k is the energy scale. It's called omega here. And so the null momenta of massless particle is parameterized by an energy scale, omega, and a point on the celestial sphere. So this is the direction or the polarization vector for the null momenta. it points all the way to infinity, cuts scri at a point, like we said earlier, and so its direction is a point on the celestial sphere. And omega is the energy scale of the momentum. So such eigenstate actually already diagonalize Lorentz rotation around the direction of the null momenta. If you just take k mu, write it in spinor helicity. So let me just write it. So this is the Pauli matrix, and you write lambda alpha. Let me write kappa alpha, kappa tilde alpha dot. So alpha and alpha dot are SL2C indices. They go from 0 to 1. There are two vectors, the spinors basically. This is some spinor helicity decomposition of the metric. Sorry, of the metric, of the momenta, of the 4-vector momenta. And rotation around this direction of the null momenta means you take this guy and rotate it by some phase. Take the other guy, you rotate it by some anti-phase. So it's automatically invariant under rotation around the null direction. But it's not invariant under Lorentz boost, which means I take k and boost it by some number, say alpha, then this guy shows up as I alpha omega k dot x. So it's clearly not an eigenstate of boost. But how do you make it an eigenstate of boost? One way to do it is to do this something called Mellin transform, this transformation, where you integrate over the energy scale omega from 0 to infinity. And this is what you get when you do the integral. So this is our new eigenstate, if you like, for the external wave functions. This guy, you can check, it also satisfies the wave equation. For example, for scalars, you can do Klein-Gordon, also satisfy that. So there's also solutions of the wave equation. So there's still on-shell data, but just in a different basis. That's okay. And when you do this, now you notice something that, this eigenstate, unlike the momentum eigenstate, it now diagonalizes simultaneously the Lorentz boost and rotation along the direction
sorry,
of the momentum.
Can I ask a question?
Yeah.
When you say boost, this k dot x is already k mu x mu, right?
Yes.
So when you say boost, you don't mean the usual kind of boost. As in,
I just mean,
k mu x mu would have been Lorentz invariant.
Yes, I just mean boosting k. Basically changing the scale of omega. That's what I mean.
Okay, I see. Thanks.
Right. No worries. Then, so this is something that diagonalizes this new eigenstate, this guy. Has eigenvalue minus delta under Lorentz boost. And it's also eigenstate of a rotation. So it diagonalizes the 4D Lorentz group, basically. Then by the Lie algebra isomorphism, this is also an eigenstate that diagonalizes the 2D conformal group. So it's a conformal primary. Well, you can think about it that way. But then, if you take on-shell, say, scattering amplitude in 4 dimensions and Mellin transform doing this transformation on each and every one of these external states, then you get something that transforms under the conformal group completely. So you can see it as a conformal correlator. And this conformal correlator, the coordinate dependencies, these z, are on the celestial sphere. Hence, the program is saying, well, you can recast 4D scattering amplitudes in terms of conformal correlators on the celestial sphere. So that's the statement. So what progress is this, proposal made so far?
Sorry. So that point on the celestial sphere, does that somehow corresponds to where the massless particle end up in scri plus?
It does, yes. So massless particle goes out infinity, cuts scri at a celestial sphere, and its orientation, you have a CP1 or S2 worth of orientations you can take.
I see.
And you pick a point, you get an orientation.
I see. Thanks.
So, but this is only for massless particle, though. Just stress that. So progress so far was basically you take 4D scattering amplitude and then try to do on-shell operations with it. So, for example, you can take soft theorems, what's it called, collinear limit, and so on and so forth. These all just means. So I'm not going to talk too much about this in the talk. If you know, I'll just say it. So you can take external legs, soft or collinear. You get some splitting function. You get some certain infinities. These are infrared divergencies popping up in scattering amplitudes in 4D. They're very well established theorems. And what people did was they just Mellin transformed these soft theorems and collinear singularities. And what they got was something that corresponded to things that acted on scri. So for example, if you Mellin transform soft theorems, you get asymptotic symmetries. Well, word identities for asymptotic symmetries for the BMS group I was talking about earlier. And if you take a collinear splitting function, so if you look at how ki.kj behaves, it's actually proportional to zij, z bar ij. So I'm just parameterizing spinor helicity in a very specific way. So I'm writing k mu equals sigma mu alpha alpha dot lambda alpha, sorry, kappa alpha, kappa tilde alpha dot. And I'm writing on a local patch for kappa, 1z, and kappa tilde I'm writing as 1z bar. So this is on a local patch of S2. I'm using these coordinates. So essentially, when ki.kj, which is the two external momenta for two massless particles in the scattering amplitude, when they become collinear, this is 0. So two collinear vectors dot each other to 0. But correspondingly, you can see this as zij going to 0 or z bar ij going to 0. And this means the 2 points on the celestial sphere, the insertion points of the conformal primaries living on the celestial sphere, they get close to each other. So that's the OPE limit, if you like, in the conformal field theory. So if you just Mellin transform the splitting functions from collinear singularities, you can get so-called celestial OPEs. That's another story. And then the third thing was these infinite dimensional soft algebras. So where do they come from? It's something that, notice in equation 1, these conformal primary eigenstates, these guys, there's a gamma function sitting on top. For those of you who know gamma functions, it has a singularity, it has a pole at delta equals 0 and then negative integers. So if you take those integer values of delta and take the residue of these eigenstates inside the celestial OPEs and do a mode expansion, you'll find algebras like what you would do for Virasoro algebra. But in this case, you find something bigger. This case in Yang-Mills, for example, amplitude, you can find this group of algebra called S algebra. So it's a Casimudi algebra with level 0, but it's an infinite extension. So there's a sub-label labeling it. It looks like JA, so this is the JB because like FABC, JC with a pole. This is the usual Casimudi, level 0. ABC here are adjoint color indices. And then there's a sub-label called delta 1, delta 2. You have delta 1 plus delta 2. So Casimudi is when delta 1 equals delta 2 equals 0. And any other delta, you see algebra doesn't close unless you include delta going all the way to infinity. So this is the infinite extension of the usual Casimudi algebra. And in the case of gravity, is something called the loop algebra of the wedge algebra of the W1 plus infinity algebra. So this is some diffeomorphism preserving algebra, which if you want, I can show you later, but it doesn't matter that much in the talk. So the takeaway of this slide is, there's been an on-shell matching, if you like to say that. There's an observation that you can take Mellin transforms of 4D scattering amplitudes and various variations of it, which are already given, computed so many years ago by the scattering amplitude people, and see it as a conformal operation, conformal field theory operation, like OPEs and so on and so forth. So this is all good and nice, but what are the dissatisfactions? So thing number one, you might have noticed, maybe not, is the space of on-shell field configurations, as in these eigenstates, compared to e to the I omega k dot x. What happened was these guys don't have singularities anywhere. They're completely analytic. They're delta function normalizable and so on and so forth. But these guys are not in any sense. So because if you look at when delta is positive, delta is generically a complex number. When delta is positive, k dot x equals 0 is a singular locus for this eigenstate. So as in, there's a codimension 1 slice on spacetime where this on-shell field configuration, these conformal primaries, are completely singular. they're arbitrarily horribly singular, but you're not accounting for that. Of course, you can just say, well, I don't care about it. I'm just going to do basis change in scattering amplitude. That's okay. But what we're here to demonstrate is if you take it carefully enough, you find something surprisingly nice. So, and then two was a Mellin transform, or these ways to define, the dual conformal field theory, if you like, there is one, are defined only for on-shell data, such as wave functions, scattering amplitudes, and so on and so forth. So it's never been defined for off-shell data. That means there cannot be a Lagrangian description of some 2D microscopic CFT that actually produce underlying conformal correlator that you're claiming is supposed to be coming from some celestial CFT, if you like. So there hasn't been any specific form of a celestial CFT generated, which intrinsically dynamically produce these conformal correlators. And the fourth thing is this whole program is.
I might have missed something. When you say celestial CFT, do you mean treating that these amplitudes generate correlation functions, and these correlation functions is a 2D CFT?
Yeah, they're supposed to be a 2D CFT.
Right, as in it is expected to satisfy all the crossing relations and so on. That is expected as healthy. And would it be necessarily unitary CFT?
No.
Okay. It's not unitary in general as a CFT.
So far, the discoveries so far are all non-unitary.
I see. But if I take a unitary CFT, does it work backwards to give anything that is sensible as a Minkowski scattering amplitude? Or
so you can do that. You can take a two-dimensional any 2D CFT of your favorite and do inverse Mellin transform. Just invert this transformation. That's doable. And then you get nonsense.
Okay.
So it doesn't really correspond to very meaningful stuff back on spacetime. Especially it's not an amplitude, where amplitude has these momentum conserving delta functions. So that's very hard to reproduce.
I see.
I'll show you what we did.
But is there a criteria when it would give something sensible and when it doesn't?
There is. So, there isn't. Is the better answer. So it's pretty much the Wild West at the moment, because inverse Mellin transform is something that it's very hard to control, and there's a very specific convergence radius. So you need to be very, very careful when you do it. And I don't think anyone knows, what it looks like when it goes back to the other side. And especially, you might notice something else, which is Mellin transform mixes energy scales, which are very small and very large. So it's UVR mixing from the 4D perspective. So it's like you took something that's UVR separated, and then you mixed all the energy scales to go to 2D. While in 2D, it's a fixed point in UVR. But when you do inverse Mellin transform, somehow you have to separate UV from IR in some way.
I see.
It's very difficult to guess or observe what's been happening just based on the calculations so far.
I see.
Yeah, but like I said, there's not been a Lagrangian description for a 2D CFT that actually generate these class of conformal correlators.
I see. Thank you. That's helpful. Thanks.
Then first thing we're going to do to address these problems is to start with number one, which is, there's a arbitrarily singular locus k dot x equals 0 for these space of field configurations. But to characterize this space of field configurations, which are singular on this locus is best described by, if you give me a k, a full vector k, null full vector, I give you a codimension one slice of Minkowski space defined by this equation. But that's not very convenient. I have to change my codimensional slice every time you give me a new k. So what we were proposing is you can promote k to a coordinate. it's a coordinate on S2 because, like we said earlier, it's characterizing the direction of some normal length in 4 dimensions. There's a CP1 worth of it or S2 worth of it living in infinity. So we promote K to a coordinate and consider a projected null term bundled over Minkowski space. So something like this. For those of you who don't know, CP1 is isomorphic to S2 once you give me a complex structure. So this space, which is much larger than the original Minkowski space, you can describe the locus k dot x very easily in this space because all the k's are there. There's a CP1 trivial fibration over each point on Minkowski space. Just think about it this way. But as a twisting theorist, you know that when you complexify the whole setting, as in complexify Minkowski space to C4, this is twisted space. So this motivates us to go to twisted space. So what can twisted theory do? Let's start with what exactly is twisted space? The definitions. Twisted space M is defined as a space of null geodesics in Minkowski space. For example, and each null geodesic in M is a point on twisted space. So something that interchanges localness and non-localness. What was a geodesic, a null geodesic in Minkowski space, for example, becomes a point on this new space called twisted space. And what is a null separated line, a point on Minkowski space become a CP1 on twisted space. And the reason behind that is just it's asking how many null geodesics are going through one single point. What's the how much orientations can I have? It's a CP1 worth of orientations. So it corresponds to the CP1 on this new space. So in the particular case of complexifying Minkowski space C4, the space of null lines is just is projective space, CP3. And so PT is defined as a sub space of CP3. CP3 you can think about it the following way. So I have starting with 4 complex coordinates. I'm calling them mu alpha dot and lambda alpha. So here alpha dot go from 0 to 1. They're SL2C indices. They're linked to the original Lorentz index by through a Pauli matrix. And now I take away the scaling of these 4 complex coordinates, and I treat them as homogeneous coordinates, as in mu alpha dot lambda alpha is identified with S mu alpha dot S lambda alpha. S is in C star, so any non-zero complex number. So after this identification, I've treated all the lines as a point on C4. It's the space called CP3, complexified projective space. And PT is just CP3 with some extra condition on it, where it says one of the coordinates cannot be 0. It's a mathematical thing, but geometrically what it means is you're considering the space of lines in R4, but not S4. It's taken away the point at infinity. Cool. Any questions here? No, I can't see any of you guys. So no questions, or is it okay if I continue, Janet?
Yes, good.
Okay, so then, as I said, this is the twisted space for complexifying Minkowski space for C4. So how do you go to any signature? You can go to any signature on Minkowski space by choosing a real slice of twisted space. And that just means you define an involution, complex involution, from PT to PT. And you look for the fixed points under this involution. So for example, let me be more specific. So you can write the 4D x mu, the Lorentz type vector representation of SL2C notation for space-time coordinate x, and multiplied by the Pauli matrices, or the first entry is 1, you get some very specific thing. This is the vector rep of SL2C. And you can define an involution on these coordinates, give it something called x hat. Induced on 2 spinors, this is the involution, some complex conjugation. And you just enforce x alpha dot equals x hat alpha dot. Then you're on real Euclidean R4. So similarly, you can go to Lorentzian signature 2, and so on. just a notational thing. Whenever I write alpha alpha dot, I mean me from now on. You just think everywhere I'm multiplying by some Pauli matrices. Cool. And then how is it geometrically related to the original 4D spacetime, as in C4? So you can start with there's a double fibration diagram basically. Don't be scared of it if you've never seen something like this before. What it means is there's a fibration of a bigger space, which is the space we actually were talking about earlier, the projective null cone bundled over Minkowski space itself. So this is the K, if you like. But here I'm parameterizing K alpha alpha dot as lambda alpha lambda bar alpha dot. This is a complex conjugate. So the map from this space, bigger space, down to Minkowski space itself is just a forgetful map where you forget about the CP1. And the map down to twisted space, though, on the left-hand side is something called instance relation, which encodes all the geometric relation between PT and MC. So to go from PT to MC, you need to go first back up to this bigger space called correspondence space, and then push down with the forgetful map. So for example, like I said earlier, a point on Minkowski space corresponds to a projective line, CP1 on PT. This is just the fact that you pick a point on Minkowski space and ask how many orientations of lines can I have? CP1 with so that corresponds to a CP1 on PT. And a point on PT gives you a line on Minkowski space, but it's complexified, so it's a null two-plane, P2. These relations, you can see both of them from this instance relation. And in particular, what we love working in to use, fully harness the power of complex geometry, complex analysis, is to be in Euclidean signature. Like I defined in the slides before, this involution defined on PT, you will have a isomorphism between these two spaces. They're actually the same. You can solve the scattering equation completely. PT becomes R4 across CP1. So it's the fibration degenerates into something like this. So for geometric intuition, just think PT or twisted space is just a space-time cross the CP1 at every single point. Then, well, that's some nice geometry. So where's the physics actually? So the physics is actually hidden on shell data, at least to start with. It's hidden in these cohomology classes. Don't be scared of that either. I'll tell you what it is. So a holistic H on shell massless field on complexifying Minkowski space. For example, a scalar phi, gluon A, spin 1, spin 0, and the graviton H, spin 2, and so on and so forth, and negative velocities, of course. These on-shell massless fields are encoded as sections of H01. So what that means is you can write H01s, they're cohomology classes, so it's a D bar, well, it's partial cohomology classes. 01 just means it's D bar closed, so half closed. Mod D bar exact pieces. So it's a 0-1 form and it's D bar closed, and you mod out to D bar exact pieces. So there's some omega 0-1 to it's a 0-1 form, say I call it omega. Then omega is D bar closed, and omega is considered up to D bar of G equals omega. That's all it means. So some 0-1 form on twisted space, and this O thing means it's twisted by some weighted bundle of homogeneous weight scaling 2h minus 2. So what that means very explicitly is, I can write on the next slide, is so say I have a D bar closed but not exact 0-1 form called psi. It's a function of all the twisted space coordinates. This is just a collective way of writing mu alpha dot lambda alpha. Then if you rescale these coordinates, they're homogeneous coordinates, remember, on CP3. So if I rescale these coordinates, the whole function rescales like s to the minus 2 if it's O minus 2. If it's O 2h minus 2, then this goes like s to the 2h minus 2. This is just indicating the homogeneous scaling of these forms. So a helicity H on shell massless field will correspond to such cohomology class in 1-to-1. So how does this work? So if I hand you now, some homogeneous weight, say 0, sorry, -2, H01 on PT, you're starting here. And I claim this is scalar on spacetime. So how do you go about doing this, seeing this? You start with the such of psi, and then pull it back with the instance relation onto this space. And then you integrate out all the possible choices with CP1. That's the forgetful map. Then you get something on spacetime. This is exactly how it's done. So you take this section of section of H01 on twisted space. You pull it back. This just means pull it back with the instance relation. So you rewrite mu alpha dot as x alpha alpha dot lambda alpha, sub it in, and then integrate over all the choices of lambda. You get something that purely depends on x. So and you can show this guy big psi actually satisfies the Klein-Gordon equation, massless one. And the gauge transformation on twisted space, something you might have noticed already, becomes these cohomological gauge transformations. So all that means is because all the on-shell fields are defined up to d bar exact pieces, so you can always take a psi, say, in H01, and take psi to d bar plus something. This is up to consideration in the H01 definition. This is d bar exact pieces. So are there any questions?
I think so far so good. Okay.
Okay, is it clear that what I mean, or are you guys following me?
I think not every single detail, but roughly the ideas.
Yeah, the takeaway here is just you can write helicity H on shell massless fields on Minkowski space at some cohomology class.
Yes. Yeah.
Cool. I'm trying to slow it down because I want people to have as many takeaways as possible. So please interrupt and ask questions if you want. I can go to arbitrary detail if you like to. So now let me clarify another geometric intuition, which is massless particle all end up in null infinity. They cut null infinity at the celestial sphere. And twisted space, you just told me, is the space of all the null geodesics. So does scri have anything to do with twisted space? Answer is, of course, yes. So scri, or partially complexified scri, remember we started with RU cross S2. We'd like to complexify U slightly by writing U and U bar. So U is x alpha alpha dot lambda alpha lambda bar alpha dot. And lambda lambda bar are coordinates on S2. X is the spacetime coordinate. And U bar will be the complex conjugate. It's the same thing. So usually it's real, but if I allow lambda bar to be sort of dabbing into the complex domain, as in B and B bar, the scaling they have, to slightly not be complex conjugate of each other, then U is slightly complex because B bar is no longer real. Then scri can be seen as a line bundle. So it's a line bundle with weight 1, over CP1. This is just referring to the fact that U is a function of lambda bar. These are the weights in lambda bar. The street legal, this is not the right way to write it. It's actually a CP1 cross CP1, but that would be full complexification. But this notation to me is, in a street legal way, it just means I'm slightly complexifying U, but not the basis. So, and scri as a metric is quite degenerate, with a 0 in front of the DU2s and the sphere usual stereographic projection coordinate. If you just write things in the way you're used to, you'll see that coming up. So d lambda is epsilon alpha beta lambda alpha d lambda beta. So this guy is the SL2C invariant. It's the thing in the lead loop. And it contracts undotted indices, SL2C indices. So, or in spinel helicity, we usually write lambda d lambda as angle bracket. So the basic geometric relation between scri and twisted space is that there's a projection. So you can start with twisted space with these coordinates. So it's the CP3 coordinates, like we said earlier, alpha and alpha that go from 0 to 1. They're homogeneous coordinates on CP3, and their complex conjugate. And the projection goes down to scri is you get some coordinate u and u bar defined by mu lambda bar and mu bar lambda and the two lambdas. So the spheres are just straightforwardly projected, and the u direction you have to contract the mu's basically. Where does this come from? Well, remember the incidence relation was mu alpha dot is x. Sorry, mu alpha dot is x alpha dot lambda alpha. So if you use the incidence relation, it's this guy. You can group either these two guys or these two guys. So that gives you mu lambda bar or mu bar lambda on scri. So now, okay, we know there's a twisted space is a much bigger space than scri, because this is space of all the line. Sorry, null geodesics. Scri is just where they end. So where's the celestial sphere then? You're trying to do some correct some statements about, there's a dual 2D CFT living on the celestial sphere. So where is the celestial sphere then on twisted space? So celestial spheres, because they're cuts on scri, so naturally you can use the map before to lift anything back to twisted space as a CP1 fiber. So remember, there are these fibers living on top of Minkowski space. Think about it that way. Or in other words, so any sphere that they're fibered over Minkowski space on twisted space, you can push it down with this map, this projection, to any celestial sphere on scri. So importantly, they have the same amount of physical information. And in particular, we're going to be interested in the celestial sphere at u equals 0. So it's the central cut. Let me show you now. Is these ones. So I should say this is u equals 0. This is scri minus. So this is v equals 0. This is retarded time. This is advanced time. It's t plus rn t minus r. So with the projection, you can see there's always a sphere at u equals 0, which is at mu lambda bar equals 0. Simultaneously, mu bar lambda is also 0. So this sphere, this celestial sphere at u equals 0, exactly correspond to this particular sphere on twisted space. So if I also know about, a rewrite of Minkowski space metric, in the time-like region, you can do these Euclidean ADS3 slices. Each and every one of these slices are Euclidean ADS3. And in this region, in the Rindeler region or space-like region, you can do another slicing, just different choice of coordinates. It's a matter of sign changes, and write these slices as a Lorentzian de Sitter theory slices, and they have common boundaries. So their common boundary is precisely the sphere at u equals 0. So basically, this upshot is you can take Minkowski space, foliate it with these ADS3 or de Sitter 3 slices, and they have a common boundary lying on the u equals 0. Well, this is precisely because I chose an origin to be at x equals 0. So the division of these slices are completely artificial. I can always move my origin to something like this. Then my Euclidean ADS3 slices look like this. But those choices, I can always conformal transform back the origin to the origin to x equals 0. Good. So any questions here or? So I'm literally blind at the moment. I can't see anyone. So if there's a question, please shout it out.
Yeah, we're good. We're good.
Okay, so this induces the notion of embedding space formalism. So what this means is you can start with Minkowski space itself, and then consider a projectivization, where you take away the scaling in Minkowski space. So that amounts to taking a symmetry direction along this direction, say. And write hyperbolic 3 space, which is Euclidean ADS3, with the following metric. You see it doesn't scale with x, has homogeneous weight 0 in x. Now x is a homogeneous coordinate as well. It's actually RP3 now. Because you started with R4, you took away the scaling, you also get a projective space. It's RP3. That's the scaling. And this is the metric, this is all the topology. And in terms of the metric, you can put this particular metric on RP3 and gives you Euclidean ADS3. or H3. And in the gauge slice embedding space formalism, you can always pick x squared, little x squared to be equal to t squared, and the first component to be 1, and recover the Poincare half space coordinate. Remember, so originally we were writing x alpha alpha dot, or the vector rep of SL2C, as some, x minus t, x plus t, y plus iz, y minus iz, that sort of thing. In this particular gauge choice, and after consider things up to real scaling and picking this particular gauge condition, you can write Minkowski spacetime coordinates as this, and you just redefine x minus iy to be z bar, x plus iy to be z, and t squared is t squared. Then this metric gives you the usual Poincare half space coordinate. So there's something like z squared, dz squared plus dz bar plus dt squared. Sorry, this is a t. So that's your ADS3 bulk direction, and that's your boundary S2. Cool. So under this, space-time scaling reduction or embedding space formalism, you can actually take scaling reduction of twisted space as well. So what that means is twisted space was the space of geodesics upstairs for this entire space. And in the Mellin region, you can also take scaling reduction because you did it on level of spacetime. You can also take reduction of the twisted space, its corresponding twisted space. And this is indeed possible, where you just take, this is the twisted space we were imagining. You take a scaling reduction on R4, you get RP3, CP1 is not touched. You end up with the metric we were saying earlier on embedding space formalism, you get H3 cross CP1. So that's the bigger space. Downstairs, it's something called a mini twisted space. Mini twisted space are also just twisted spaces. They're space of oriented geodesics of 3D spacetime. In this particular case, hyperbolic 3 space. So again, there's a double vibration because everything is just inherited from the previous one we were seeing before. So it's still a forgetful map. And then to the left side is still an instance relation, but now x is considered up to scale. So you just, the coefficient of this instance relation is considered up to scale. This is the mini twisted space of Minkowski space. So now it's a CP1 cross CP1, modding out some diagonal CP1. So here, CP1 cross CP1 means mu and lambda, instead of being homogeneous coordinates on CP3, that was before. Homogeneous completely means if I rescale, this is Zi, I call them collectively, they rescale with the same scaling. So if I rescale Zi to S times Zi, these are scaled simultaneously. They have the same scaling. But now mu and lambda have independent scaling. So mu is allowed to scale on its own. Lambda is allowed to scale on its own. That's what it means. It's a quadric inside CP3, this thing. Okay, so that's all the twisted theory machineries. So for those of you who didn't like it, or it was the first time seeing it, it's okay. I'm not going to use too much of those. I just want to give people a gist of what's going on for these twisted spaces and so on and so forth. And actually doing celestial holography is the next step. So let's motivate something first. So this Mellin transform, remember at the beginning, was defined as something like this. You integrate over the energy scale from 0 to infinity. So another way to see it is to see it as a scaling reduction. So what that means is you can rewrite this integral. So first take this guy, take your momentum eigenstate, expand it in power series in omega. So I write it as I can go from 0 to infinity, omega to the n. But this is just let me write k dot x, momentum eigenstate for a scalar. I can expand it in power series in omega, and take this omega and bring it forward. So it's the sum over n, 0 to infinity, and some I k dot x to the n, or n factorial. And then I can rewrite this n as some d by dx, because it's a scaling in x, essentially, in each term. So something I can do is to write e to the log omega delta plus x dx. So I write the Euler vector, which measures the weight of this homogeneous function. And then I resum this n. You get something that's doesn't depend on omega anymore. You just e to the I k dot x, leaving in front some d omega 0 to infinity, e to the log omega delta plus x dx. So what this is telling you is a Mellin transform is selecting the eigenstate which scales like its weight minus delta in x. And that's indeed what was happening. We saw that for momentum eigenstate, you'll get things like k dot x to the delta gamma delta. There's indeed selecting an eigenstate that scales in x, like x to the minus delta. So this is a definition for on-shell state, which we interpreted in a slightly different way. So we'd like to define the Mellin transform for off-shell states in exactly the same way. So please ignore this. I think it's a bit too much. For off-shell states in exactly the same way, where you would start with a generic function or a generic field, which is off-shell, and integrate over its energy scale just amounts to selecting the part of the off-shell field that scales like x to the minus delta. That's the goal. But from an embedding space formalism point of view, this also just means that when you pick a part of the field that scales like x to a certain number, that means you're taking a scaling reduction along some direction. So you're taking mx, Minkowski space, and considering it up to scale. Then in this downstairs space, let's call it m tilde x, which is embedding space of x. Sorry, embeds in mx. Something that scales like x to the minus delta on this space will just have a label delta on this space. This is the famous, so dilatation weight becomes projective weight upstairs. So that's the dilatation weight. That's the projective weight. Is that clear? So geometrically, what Mellin transform is doing is just amounts to, you take your Minkowski space, if you like, and you do a scaling reduction for off-shell fields. And then it's compensated by some number delta, which tells you how your field was scaling in x back upstairs in Minkowski space. Okay, so now I've told you about all these things in twistor theory, how on-shell data is collected, and how the geometry works, and so on and so forth. So is it possible to take it off-shell, these on-shell data on twistor space? So because we know how to do Mellin transform geometrically now on shell field, so can you write down an on-shell function on twistor space such that it gives me some dynamics, produces dynamics of these H01s? Answer is of course yes. Sorry, Jen, is there a time constraint or?
I think there's no strict time constraint. The quick answer is, but I also want the rest of the audience be able to get the gist of your talk. So how about
Sure.
that you try to get the gist out within 15 minutes, and for people who are more interested, they can stay on and listen to
Sure.
more detail. How about that?
Okay. Sorry about that.
No.
Yeah, I was trying to be
okay.
as explicit as
I
possible.
think it's very clear.
Yeah, I know.
That's wonderful.
Yeah, I know twistor theory is a very niche subject. Not a lot of people in contact with it. Also, the algebraic geometry used. So, anyway,
so it's very clear. But I just don't want people to leave before they get the point.
Sure. Let me be quick then.
Okay.
I'll get to the point. So you can write down these action functionals on twistor space for integrable theories very easily. For example, self-dual Yang-Mills, self-dual gravity, so on and so forth. And you can do off-shell extensions of them very quickly as well in this form. So the upshot is that you can write Yang-Mills, Einstein gravity, conformal gravity, scalar, all of these theories on twisted space as an off-shell function. And their equation of motion enforces the fact that on twisted space your fields are on some H01. So this is a sort of twist actions you would be considering, things like this. And okay, I'll jump this. And so now we're ready to go back to the Slash-Hole holography shebang and apply the ideas we have just talked about. Let's reiterate the issues. For those of you who are interested, you just need to look at the slides. So the issues were, space of on-shell configurations were not incorporated. They're particularly singular on this locus, k dot x equals 0, and when delta is positive. And so half your spectrum is singular. And we sort of solved that by going to twisted space, as in describing a locus better. We went to twisted space, promoted k to a coordinate. And 2 was Mellin transform was only defined for on-shell data. So we know how to define for off-shell data as well. We just do a scaling reduction and compensate it with some number. And the third thing was there were no Lagrangian description of a microscopic 2D CFT. We're about to rectify that. So the way to do it is, well, as in the first thing was we consider this larger space called twisted space, where we promote k to a coordinate to better describe the locus k dot equals 0. And then to prepare ourselves for these, arbitrarily singular on-shell field configurations in the QFT, what we do is you need to actually allow these extra field configurations. And in QFT, as you know, the space of on-shell configurations have to be compatible with boundary conditions and gauge transformation, like in Dirichlet, for example. So we actually add all these extra field configurations by doing a very special gauge transformation. And on the level of path integral, something miracle happened. And then after that, you prepared your theory to be ready for these extra on-shell field configurations. Now on the level of action functionals, I can do Mellin transforms because my theory is already ready for these on-shell field configurations. They are allowed to be singular. Then I do Mellin transform on my off-shell action functional, which geometrically we just interpreted as a scaling reduction in X, and I trade that for some number, this delta. Then you'll see out pops an action functional which gives you some 2D CFT living on the celestial sphere at u equals 0, as we were saying. So here's the roadmap for self-dual Yang-Mills, for example. I'm just taking one example. So you can take self-dual Yang-Mills, lift it up to PT in the way I glossed over. You can trust me, there's an action functional on twisted space that gives you self-dual Yang-Mills. And you do this on the level of path integral. You do some large gauge transformations, these special gauge transformations, and do a field redefinition. Then you'll see that action formally splits into 2 parts, and you can do a geometric Mellin transform. So up to here, I was just preparing the theory for the on-shell, the singular on-shell states. And here I'm doing Mellin transform. So I'm literally just doing celestial holography as carefully as possible, if you like. Then out pops some 2D CFT very naturally. So I'm going to gloss over
I did
this.
not get the point where the off-shell stuff comes in this roadmap. Okay. Which part is where you introduce the off-shell things?
Step 1. So I'm starting with an action function. It's generically off-shell.
But then in this whole story, how does it change with and without the off-shell? Before you had the off-shell things, you still get a 2D CFT. Then you still get a bunch of correlation functions of the 2D CFT. And now what has changed? But
I don't get the 2D CFT though. There's no 2D CFT telling me that generates how to generate this correlation function. It's only defined on-shell. There's no off-shell 2D CFT. As a QFT person, or as a holographer, in any sense.
Let me see.
That's not satisfying.
When you say the CFT is on shell, previously you wrote down correlation functions of the 2D CFT, right?
Yes.
When you have a correlation functions of 2D CFT, what does it mean that these correlation functions are on shell? Correlation functions.
On shell just. It's just literally a correlator, so you can write it down. For example, at 4 point, it just gives you the answer. There's no way to compute it.
And now, when you say off shell, what is the thing that that you're computing?
I'll show you.
Oh, okay. Sure.
It's an action function. It's a Lagrangian.
Okay, so you're recovering the action of the CFD. That's so.
Yes, and yeah, I'll get to that part.
Okay, good. Okay, thanks.
So I'll skip the derivation as well. So like I said, this is the roadmap. You just literally do some path integral manipulation, prepare your theory, your off-shell theory, action functional to be ready, and then you do Mellin transform, but geometrically. Then you odd pops it to DCFT. So this is the first principle derivation. We don't do anything. There's no assumptions anywhere. We're just literally doing what we're supposed to do. I'll jump all these and get to the point, which is here's the 2D CFT. So this is the one for self-bool Yang-Mills. So it's some sum over the mode number delta, and then an integral over this particular CP1. So there are these on-shell free fields, off-shell free fields, eta tilde, phi tilde, and here these two terms are their connected terms. And these are coupling terms, where these J's and J tildes are bilinears and mass terms in these free fields. A's and B's here are the bulk gluon modes, A prime and B prime. So the labels here, the deltas you see, are the result of the scaling reduction. So I did a scaling reduction and I traded it for a number. So that's the Mellin transform geometrically, if you like. And if you just look at this action, it's very, very simple. And if you just take the OPE, because I'm giving you the contraction rules between phi tilde and eta tilde, you can take the OPEs between J and J tilde, and this is what you find. This is the infinite extension of level 0 Casmudi we were mentioning earlier. So we only focus on delta 1 plus delta 2 is not 0 vector. This term is actually not there. So that's the infinite, that's the S algebra. It's the infinite dimensional soft algebra people have discovered before. You recover it with no effort, basically. You can also compute the stress tensor. This is something that has bothered people for a long time, and you find indeed.
Can you go back a little? How did you recover this algebra? I missed. I got one moment of distraction. Missed it.
Yeah, no, you just literally compute it. So J is let me write it for you. J is eta tilde plus phi tilde, roughly. And J tilde is written down here.
Oh, okay. You read
off from the eta tilde.
You read it off from the action that you derived.
Yes. Yes.
Sorry. And when these eta and phi, where did they come from in the computation?
Right. So that's because I've skipped the parts. So eta tilde and phi tilde, there's something called large gauge parameter. So there are gauge transformations, for example, Yang-Mills. There are gauge transformations that doesn't vanish at infinity.
Oh, okay.
They're controlling that degree of freedom. And eta and phi are just, because I did a scaling reduction. They're just scalars coming from the reduction.
So when you started with this off-shell or self-dual Yang-Mills, you did some large gauge transformation at the infinity. And then after you essentially do some Mellin transform and kind of like integrates out those degrees of freedom that you started with, and you're left with this. Is it roughly?
So I did a large gauge transformation. I introduced these degree of freedom at infinity. And the Mellin transform is not integrating out any fields. It's integrating out a direction, a non-compact direction. This is scaling reduction. Because for off-shell field, both on-shell and off-shell fields, Mellin transform is defined as selecting the field, part of the field that scales like a very specific delta. So when you do a reduction, that means you're picking all the possible deltas, so all the fields component that scales like x to any number you like. That's the gist.
Okay.
That's what we're doing here. So you trade a direction for the label, basically.
Okay, I see.
Is that okay?
I
Yeah.
see.
So essentially, I can. Okay, later maybe.
Yeah, I'll ask you more
just to
about
get to the
these
gist.
details later.
So,
but at least I have an idea of where these things came from. Okay.
Right. And then so with the explicit description of a CFT, you can do stress tensor computations, and you find central charge is actually infinite. Not a surprise, because flat space doesn't have any scale. So central charges has to be either 0 or infinite. Because the case is infinite. But and also we started with self-dual Yang-Mills. So it's a theory that lacks is an integrable theory, and we also canceled from gauge anomaly. So there's actually no amplitude. There's no observable in this theory. So to get things more juiced up, we need to deform the 2D CFT. And we write down deformation operators, which are marginal for it. And this sources 2-point functions in the CFT. You can compute it, and you find things like this. And you can, because the OPEs, with this 2-point function, you can keep building up multi-particle or multiplicity conformal correlators. And indeed, you find MHV form factor. So this is the famous Park-Taylor factor in Yang-Mills, 4D Yang-Mills, for example. And this can be done for any multiplicity, any helicity grading on tree level. You can add deformation operators to the CFT we got and just use the OPEs we have to rebuild 4D, part of the 4D scattering amplitude without the momentum covariant delta function. That's the observable mesh. And then we also run this program for Einstein gravity. You can also do it, where now there's a little higher layer of complication, which is the theory is not completely localized on this particular celestial sphere, but it's localized on scri itself. So it's a smear over scri. So this is a demonstration. I'm just drawing a quarter of the Minkowski space diagram. That's the actual diagram. That's the origin. And in Yang-Mills, it was localized on this particular sphere. In gravity, it was smeared along scri. So fields are allowed to extend all over scri along U. But the content looks almost exactly the same, except this Poisson bracket, which I won't dwell upon. And you can similarly, these are the bulk gravitons, positive and negative velocity, and there's some explicit coupling between them and some current. And you can again just take contractions between these J's and J tildes. What you'll find is unsurprisingly the L if W infinity algebra. So it out pops very naturally, the soft algebra. And you can also compute the stress tensor, this particular form. Anyone who knows 2D CFT will be able to do it. And you can write, exponentially the stress tensor, so it generates some sort of diffeo transformation, and indeed it does. So is your diffeo. So it transforms T transforms the coordinate Z to some epsilon function of Z and Z bar. So it's some diffeo generator. And on top of that, you can also do marginal deformations like in the Yang-Mills case.
One question, I missed the point again. Yeah. Where did gravity come in? How did it show up?
Right, I changed gear completely here.
Oh.
I'm saying, so you can run the same program, the same set of configurations and program for Einstein gravity as well. And this is the 2D CFT you get.
I see. So you're kind of deriving the CFT dual for Minkowski gravity. That's roughly what you're doing.
That's right, yes.
Okay, brilliant. Thanks.
Yes, starting from the 2D CFT. Starting from the self-dual sector. This is for the self-dual sector, and you have to do deformation to see observables, like in the Yang-Mills case. And if you do this particular deformation, then what you see is it produces MHV form factor. So this is a square of the Yang-Mills one. This is a double copy relation for people who know amplitude. Yeah, but anyway, that's, I think, the end of my talk. Sorry to take 15 minutes extra. I think I'm on time according to your 15 minutes instruction.
Right. I certainly will go back in the slides and ask you more questions, but let us see if there are questions from other audience.
Yeah.
Okay. If there are no other questions, then the rest I think is some bonus hours, and I would like to go back a little to see what
Sure.
happened to the self-dual.
Yeah.
What exactly has been done to get this 2D
Sure.
path integral? But I
Sure.
have a
Let's do that.
question. Is it
Mhm.
so that there's no guarantee that the CFD is it a guarantee that the CFD will automatically, if you derive it that way, would automatically be, let's say, a modular invariant CFT, or
It will be. Yes.
uh,
It's guaranteed.
okay, it's guaranteed. In which step is it guaranteed?
So because you started with the Lorentz invariant theory,
Oh, okay, okay,
then you end up with the conformal invariant theory.
okay.
Yeah.
And then one other thing that I also didn't quite get is, if the bulk theory, I'm working in a semi-classical limit, right?
Yeah. Yeah.
But then the CFT is fully quantum.
Right. So let me say this. For self-dual theories, they're one loop exact.
Okay.
So that means yeah, I guess people know what that means. So they're one loop exact. They have a gauge anomaly on twisted space. They have a one loop amplitude, all plus. And we add a term, which I skipped, to cancel it. So it's anomaly free, this one. This is
okay.
some generic holomorphic CFT stuff. Sorry, holomorphic QFT stuff. We add this extra term to cancel the anomaly that also cancels the one loop amplitude. So after that, your theory is fully consistent on the quantum level.
Okay,
So
but when it comes
and
to
this,
gravity, can I still say the same?
you can still say the same. So self-dual gravity is also one loop exact,
But then do
and you can
I?
also add.
But in the self,
You can also
sorry.
you can also add a similar counter term to cancel this one loop all plus amplitude. So it's also a quantum mechanical statement.
I see, but in
The
the
action
case
function that
of
we started with is
gravity,
quantum.
do I have to worry about summing over other topologies, or?
You don't, because this is the magic of twisted space, if you like. So the level of path integral, usually, in gravity, it's very hard to quantize and so on and so forth. But at least for self-dual gravity, you can have this anomaly-free lifting up to twisted space, where all the diffeos, which are usually infinite dimensional group, on twisted space, it becomes some cohomological transformation. Like I said earlier, so your H, your graviton, in this case on shell, is an H01 on PT with weight plus 2. So H, usually you would say generates diffeo, right? But here, H is just considered up to some d bar of G, infinitesimally. Of course, you need to consider some covariant D, but okay. So essentially, the upshot is any diffeo transformation in gravity is translated to some cohomological gauge transformation on twisted space, and that becomes very simple. So it's not any different from Yang-Mills from the perspective of twisted theory.
I see. In which case, okay, maybe it is a good point to go back to a bit of more details of what did you do in the case of, let's say, self-dual Yang-Mills to get all the way to the CFD.
Sure.
All right.
Sure.
Yeah, because
Sure.
I knew that people would leave at 15 minutes past the
Please
talk,
do.
and I think it would be a pity if they missed your punchline.
Sure. Sorry about that, you guys. I was just trying to get through as much detail as possible. Sorry. As long as you don't have to listen through the whole talk, but just for me to promote twisted theory a little bit, because it's such a niche subject, nobody knows about it or care about it. We're just trying to say it's very useful in this particular scenario. Anyway, so yeah, the steps are as follows. So let me tell you what a space-time large gauge transformation is. So a large gauge parameter, G, so you can do an asymptotic expansion of the curvature, Yang-Mills curvature, F mu nu, say, in orders of R. So it will look like order 1 over R plus order R0 and plus higher orders, which are vanishing. Sorry, which are blowing up. at infinity, and then it's just picking the leading one of RPs, and it's demanding the fact that there's a finite energy condition at infinity for flat space. So that means if you integrate over the entire space-time, energy shouldn't be infinite. So that means whatever your leftover curvature here has to be 0. But when you do an asymptotic expansion of the A's, of the gauge fields, that means you get something pure gauge. So whatever it contributes, its field strength should be 0. And this is precisely the sort of thing you do, where the residual, just think about this, the residual gauge degree of freedom living at infinity is these radiative data called A mu, and they're pure gauge, so their field strength is vanishing. And you can do a gauge transformation for these guys asymptotically. The gauge parameter are these G's. And the d mu G's, they take a very specific form. So remember, they have to contribute nothing to the energy scale. So they're pure gauge. They're a derivative of their own already. So this is the gauge parameter G, and that's the gauge transformation we do at infinity. This is very well established, I think, since many years ago. Something called a large gauge transformation. In gravity, you just do a very similar thing where you have two derivatives acting on something, where that's a graviton mode at infinity. It's labeling the radiative data, basically. And it also contributes 0 curvature tensor at infinity, just this is the asymptotically flat condition. In Yang-Mills is finite energy condition. But this, this mode, large gauge transformation, you can also lift it back to twisted space, and it will look like this. It's a very shocking expression, I know, first glance. But all you have to take away is the following. So there's some free functional controlling this gauge transformation, and d bar of it, that's the cohomological gauge transformation bit. When you actually compute what d bar of this means, so let's do that very briefly. So this can be a d bar lambda or a d bar mu. This is the d bar in d bar lambda plus d bar mu. That's the twisted space d bar. Then you're taking derivatives, essentially taking derivatives with respect to lambda hat and u hat. Then what you get is you can be a lambda derivative. So I claim it only hit this guy. It increases the order of the pole. The first term looks like whatever these craps are. Second term is when d bar can hit lambda tilde, sorry, eta tilde as well, with a simple pole. And then the third term, which is the most important one, when d bar points in mu and hits this guy. So this is something called a holomorphic delta function. And you get this guy, basically. You get 3 terms. And here, this d bar, what I mean by this is, so in complex analysis, you can take a d bar of 1 over z. Z is some generically complex number. This gives you some delta bar of z. It's a holomorphic delta function. What it means is you can integrate it, say, against easy to prove for a holomorphic function. So if you do that integral, then integrate by parts. Take this guy, integrate by parts. Because it's a holomorphic, then this is actually a total derivative. Becomes a contour integral around z equals 0.
Right. Yeah.
Yeah. So Cauchy's theorem tells you that your f is 0. Sorry, your z is 0. So it acts like a delta function, basically, in complex analysis. So that's exactly what's happening here. So I'm just writing d bar mu of 1 over mu, essentially. So it's a delta function.
Okay.
Yeah. But notice something. So in these 3 terms, there's one that contains a delta function and 2 with the higher order poles in mu lambda bar. But now if I do a field redefinition, let's see if I write it. That was a bunch of crap I was writing. Let me just copy paste that. So for a gauge transformation on twisted space, if I do this large gauge transformation on twisted space, I take A going to A, this is the covariant D, d bar is d bar plus a. So I do this, then I get all these stuff plus a wedging into the eta term. If I write it out, then I do a field redefinition, which incorporates this term and these two terms. I call that A prime. Now A prime is something with a double pole, mu on bar, something with a simple pole, and then some other term. And only leaving out this term, which has a delta function in it. So what I've done so far is, if you remember, originally the A's on twisted space, they didn't allow, I'm just assuming is Fourier decomposable on shell. So they're just momentum eigenstate, essentially. But now my A prime is all these stuff plus A. So these are Fourier decomposable, and these extra things are singular. Mu lambda bar equals 0. And to compensate for that, I'm also getting an extra term, which tells me this term, which tells me there's some dynamics living precisely on this locus. So essentially, I'm allowing extra field configurations for A, which are singular on this locus. And the system's response to me is to give me an extra system living on this locus, mu lambda bar equals 0. But mu lambda bar equals 0 is k dot x equals 0 on spacetime. So in this way, what I'm doing is I'm adding these extra field configurations, which are singular on k dot x equals 0 by hand through a field redefinition. But these A primes now have these extra field configurations. As a response from the system, it's giving me some extra system living on this locus, mu lambda bar equals 0. As you saw earlier, I showed you earlier, the 2D CFT precisely localizes to this locus. And that degree of freedom is controlled by this large gauge parameter. Is that okay?
Yes.
Yeah.
So far, so
that's that's what we did. And then if you do this gauge transformation, the set of gauge transformation for both A and B, then self-dual Yang-Mills action on twisted space naturally splits into two parts. As in, so originally you start with some action that looks like this. Trace B wedge F of A. So F here is D bar A plus A wedge A. Holomorphic part, the 0,2 part of the curvature. This is the action you start with. And you do these gauge transformations, do the field redefinitions we were talking about, then you get one piece of the action, which is just a field redefinition of the original one, where A's and B's are replaced by A prime and B prime. And you get a second term, which contains the delta function, unsurprisingly. So this delta function, you can perform some of the integrals against it, which sets mu lambda bar equals 0. That will reduce the dimension of the action, because it's a complex delta function. This is a 3 complex dimensional integral. This guy will take it to 2 complex. And the Mellin transform takes it 1 lower to it, because it's a scaling reduction. You end up with some 1-dimensional complex space, which is a CP1 at mu lambda bar equals 0. That's the where the whole thing came from. But to justify that on the level of path integral, we actually didn't do anything essentially, because you can see the split action as a sum of the original action, but with fields relabeled, and this extra piece. We call it the response action. And you can compute correlation functions with respect to the split action, so the full thing, this thing. And through some path integral manipulation, you'll see, because the redefinition is essentially additive, the measure doesn't change and stuff. It's the same as computing correlation functions with respect to this action. So large gauge transformation is essentially trivial, but it manifests the action itself as a piece of the action that allows some extra field configurations by doing this set of gauge transformations. But in the meantime, in a QFT, you also need to put corresponding boundary conditions. And this action precisely shows up as boundary condition. It's the dynamics of the boundary condition. It's these fields. And then you do a Mellin transform, which just tells you it's a symmetry reduction, and you give every field a label.
But the Mellin transform is done to what thing? Now you have a path integral.
Yeah.
To the action?
It's done, yes, to the action,
I
to every
see.
single
Okay.
on-shell field.
I see.
Yeah. Instead of sorry, off-shell field. Instead of just taking whatever is on shell, the amplitude, the wave function, and throw them in the Mellin transform, you can also do a symmetry reduction on the level of the action.
I see.
And that's what we did. It amounts to trading a direction for a scaling. So you see all these delta popping up. I can go into more details. So for example,
So they are
f
kind of like
x,
poles that you pick up, or
they're not poles. They're just a label.
I see. But what
So
determines the spectrum of these deltas here?
so that will have to be renormalizability. So
Okay.
we have to choose such deltas
Okay.
in Z plus IR. So in the celestial holography literature, what people usually make a fuss about is very specific deltas, like delta in 1 plus IR, which is the principal series of SL to Z, or delta equals 0, -1, -2, which are the soft poles, right, where the gamma functions have poles. But here we include both of them, basically.
Okay. And they would show up as conformal dimensions of operators in
Exactly.
the dual theory, right?
Yes.
So
yes.
it means that but this spectrum, is it determined by the dual? I'm a bit confused where it pops out from. As in, did the dual self-dual Yang-Mills already knows about these deltas, or at which step this information pops up?
Let me write it for you. So the basis decomposition. So say I have a phi of x on spacetime. It's very simple. There's no mystery here. It doesn't have to be self-dual Yang-Mills. Just in any field theory, you can do it. So if I want to select the scaling x, I can do the following. So this lives on, say, x is a coordinate on mx, and I'm going to write x tilde as coordinates on x, mx tilde.
Mm-hmm.
And this is the defined as mx considering x up to scaling.
Mm-hmm.
Right. Then how do I write this guy as some phi of x tilde? And so it's simple. So just write phi of x is x to some power.
Mm-hmm.
Let's call it delta. With phi labeled by some number delta. This is the scaling x, because x tilde doesn't have any scaling. I've taken away the scaling. So this is precisely the embedding space formalism gist.
But would
where,
that mean
yeah.
the CFD always have the same spectrum, regardless of what bulk theory I work with?
No, it depends on the fields and interactions.
Okay. But as in what delta would show up?
Yes, that'll be correct. It will always contain all the possible deltas.
Okay, I see.
These numbers. It's not compact.
So it means that I won't get anything that is, it's certainly not rational, and probably not, and it's not even discrete in general.
It's not discrete. It's continuous for sure.
Okay, I see.
Yeah. I admit it's incredibly weird. I agree with that, but it ends justifying means in some sense. The CFD does all the job for you, so it can compute anything people have computed before it with ease, and it can compute things people never managed to compute.
I see. And have you got to the part where there is the action of the 2D CFD?
Yeah, that's the action.
Okay, I see. Right. I see. That's after doing the Mellin transform. That's what is left.
Yes. Yeah, you do your
okay.
large.
And so there's also an infinite number of fields.
Yes, exactly. That's why
continuous spectrum of fields. So
yes.
I see.
Exactly.
But it is quadratic.
In what way?
It looks like this action is it Gaussian or
no, it's first order.
Oh, okay. Then it would be exactly solvable. Is that the point?
Exactly. Yeah. You can know everything about this theory.
Is that because you're working with self-dual Yang-Mills, or why is it that it ends up being exactly
Yeah.
solvable?
That's the main reason. So because self-dual Yang-Mills is an integrable theory, it in
Uh-huh.
itself there's an integrable hierarchy in itself.
So if the
is
if you start with some other theory in general, it could be interacting, as in it is not exactly solvable or look even better than Gaussian.
it is interacting still.
Uh-huh.
So the theory you start with, this is a limitation of the framework. The theory you start with has to be twisted space upliftable
Okay.
to start with. So all these machineries, like why can we do gravity with ease, for example? Why can we do self-dual Einstein gravity and the deformations to get full Einstein gravity? Reason is we don't actually see diffeomorphisms on twisted space. You only see gauge transformations, which are cohomological. If that condition is out of the window, then you'll have to deal with the usual thing. It's a gravitational path integral. I don't know how to do that. So whatever you do has to be upliftable to twisted theory, to twisted space. But this already includes a large class of theories.
I see.
Interesting ones. Yeah. From a bottom-up approach, this is fairly decent amount of theories. And the other thing is this construction only works in 4 dimensions.
Right, because you use twisted space.
Yes. In 6 dimensions, maybe it will work. 8 dimensions, I think it will work. In 4K dimensions, it will work.
Okay.
But in 60s, 10D, it might not. It might work as well. I don't know. But in odd dimensions, it almost certainly doesn't.
And
you have to do.
Yeah. So the bulk theory has to be some kind of gauge theories for one to do large
gravity.
gauge transformation.
Or gravity.
Right. And so all the high spin theories.
You can do that, yes. You can do high spin theories as well. You can do conformal gravity. But you always start with the integrable subsector, which is the self-dual sector.
What controls any couplings in this CFD? Is there any couplings at all?
So there is a coupling. The coupling is hidden in these guys, in the J's, definitions of the J's. I didn't actually write it down, but this essentially is inherited from the Yang-Mills curvature tensor.
I see.
Yeah. So the coupling, if you like, this is if you want to call this a duality, this 2D CFD is a weak dual to the bulk theory.
Right.
So it has exactly the same coupling as the bulk theory.
I see. And the central charge of this guy
is infinite.
Oh, it's infinity. I see.
Because this is just because the size of the CFD is infinite. If you regularize it somehow, say I take a truncation of the spectrum, and then you compute everything, then the central charge is proportional to the truncation, volume of the truncation. But your volume is infinite, so it's infinite.
I see. But is that but in the examples where people study these celestial holography, are they do they all implicitly have infinity?
So you can sort of deduce it from some of their calculations because they don't really have a form of a stress tensor. We do here, right? You can actually do computations with it. But if you don't, you can infer from the symmetries. Like, for example, like I was saying earlier, you can take the soft theorem in the book for Minkowski space scattering amplitude, and you do Mellin transforms, then you get some word identities for these asymptotic symmetries. In particular, if you do it with a soft graviton, so a soft graviton theorem, leading one, subleading one, gives you so as in you take psi. This is a graviton amplitude thing in 4 dimensions, and you take one of the psi's soft. Then this produces for you some divergent factor with the rest of the psi's. Right. And if you Mellin transform all of these, this guy becomes something like a stress tensor. So it gives you a simple pole with a dz. plus a double pole. Double pole or simple, I can't remember. And some conformal dimension measuring thing. So it behaves like a stress tensor. Behaves like a word identity of stress tensor.
Oh, right.
And yeah, so then you can try to take two such graviton soft and see what happens.
I see.
That amounts to taking TTOP, dual theory, and they claim they find infinite as well, but I haven't. It's not a computation that you trust 100% because even in 4 dimensions there are these ambiguities when you take consecutive soft limits. There's an ordering problem.
I see. And going beyond the self-dual sector, any
yeah. So you can't do that. You can do that with these deformations, because as I said, the self-dual sectors, especially after we canceled the gauge anomaly, it doesn't have any amplitude. There's no observable to compute. It's a trivial theory. So to go beyond that, you have to do perturbations. In 4 dimensions, this amounts to these anti-self-dual perturbations. You can add that and you get Fourier.
I see.
So this is some slide I missed, but if you want to tell. So in the 2D CFT side, you can also do this. You can do some marginal deformations, like so. This is just one example I wrote down. And they source these non-trivial 2-point functions. And because J and J tilde have OPEs, like we computed earlier, you can keep stucking J's to this correlator. And OPEs will tell you what the correlation function at higher multiplicity look like. So for example, with 2 J tildes and rest J's, you get correlation function of this type. This is the famous Park-Taylor factor. It's the MHV. Yeah, it's the MHV amplitude part, the kinematics part of the MHV amplitude. You reproduce that. And on top of this, you can also do it for n MHV, n to the k MHV, for any configuration of J and J tilde, any number of J, any number of J tilde. Via deformation, you'll be able to see all of them.
I see.
Compute all of them.
Yeah. I see. Okay, now I have some idea what's going on. Do you have other things that you want to tell us?
Other things, is in along the line of this project, or
is it roughly you have said most of the things that you plan to say?
The rest is ongoing work. Yeah, I think I've said most of the things I want to say, and the ongoing work. This framework is very general. So, there's also a geometric thing I can tell you guys. Here, so remember, what we were doing was Mellin transforming or scaling reducing the theory in 4 dimensions. The geometrically on space-time, what was happening was each of these slices, you can have a theory after Mellin transform. But these are, remember the action split it into 2 parts, right? There was one piece living in 3D, one in 2D. This was the thing we focused on just now, 2D CFT. The 3D thing were these theories. They're just Mellin transformed action functionals in 4D. Back in 4D. You just take your 4D action, you do Mellin transform after you allow proper field configurations. The on-shell field configuration of these 3D theories allow the singular fields on this locus on k dot x equals 0, as we said earlier, through a large gauge transformation. So these are just Mellin transform theories, and the 2D theories live here on this particular selection split. So geometrically on space-time, what's happening is you're sort of summing over a bunch of ADS3 series and DS3. But they have a common boundary, which is on this particular celestial sphere. So essentially, it's the idea De Boer and Solodukin had. It's something called holographic reduction. They want to think about flat space holography, if you like, there's such a thing, as a integral version of ADS3 CFT2. And
but this is a code kind of reduced by 2 dimensions.
Yeah, but the actual duality is actually happening with each delta. You label a theory here.
Oh, okay, I see what you mean. I see.
Yeah, and I'm summing over all the deltas. That's one of them.
So the full, so even though we say we have reduced by 2 dimensions, there's actually also an infinite number of theories. So
yes,
that is living on this codimension 2 surface.
There's infinitely many copies of this theory, and each and every one of them correspond to an ADS3 slice.
I see. Now okay. So it is. So as in, this can be phrased in a more similar form as the usual ADS-CFT. But then, since I have an infinite number of ADS slices, it leads to an infinite number of theories on this codimension too.
Yeah, that's right. But the miracle thing here is the infinite number of 3D theories. They resum to give you some theory in 4D.
I see.
That's the non-trivial thing.
Okay, so they have done something. They have done some transformation to turn the 4D theory, turn it around into a sum of 3D theories, and it is still a Mellin transform.
It is a Mellin transform. Okay. Because if you just take, I mean, you for sure know ADS better than me. The first paper we wrote was on ADS3 CFT2. So this guy, another way to see this is the ADS3 bulk to boundary propagator.
I see.
So when you do Mellin transform, 4D amplitudes just become a 3D. So that's what you're doing. You're just computing Witten diagram, essentially. Each eigenstate is a bulk to boundary propagator.
I see.
But it's always just contact. We compute these Witten diagrams with mini twisted space methods in the first paper. That's where this whole idea came about. And then the second paper was about Yang-Mills. We derived a CFT, and then third paper was gravity. Einstein gravity.
I see.
Yeah.
Hey, thank you. Are there other questions from other audience? I can see that there are some celestial holography people. Do they have other questions?
So I should state, make a statement. This is our understanding of celestial holography.
I see.
You can have your version, but this is our understanding. And with this understanding, you literally derive something useful. That's the upshot.
Right. As in, you derive the dual theory out of the bulk theory. I think that's right. That looks very cool.
So in some sense, you can say this is like a Chern-Simons WSW type correspondence. But what's weird is this dual WSW type thing. It also knows about diffeos. Mm-hmm. So for example, the one in gravity, you can compute the stress tensor and knows about the residual S2 diffeomorphisms acting on the sphere, which is very cool. It's something that so WSW is like a boundary response from labeling boundary conditions for Chern-Simons. This is also similar in a way because the dynamical field we're seeing are also
a large
just
gauge transformation. Indeed, yes.
Yeah, they labeled the infinitely degenerate vacuum at infinity as well. In the celestial literature, they call them the Godestone. So essentially, you have this BMS symmetry acting non-trivially at infinity, and picking a particular vacuum. So BMS just transits you between different vacuums. So they're all pure gauge stuff at infinity. And you know, because it's pure gauge, you can pick any gauge field you like as long as they're pure gauge. There's an infinite degeneracy of the vacuum at infinity, both for gravity and Yang-Mills.
It is a BMS group Wessel-Witten theory, can
I? I don't think so. So Wessel-Witten doesn't. So BMS is bigger actually than the bulk symmetry. As we said in the beginning,
that's also true.
They were trying to look for Poincare or subgroup Poincare, and they found some infinite dimensional group. Whereas WW is not. Its symmetry is sort of contained in the Chern-Simons. It's much richer, this theory.
But then at the boundary, it got promoted to Virasoro or Kac-Moody.
Yeah, okay. I agree with that. Yeah.
Okay.
But the thing is, so these BMS symmetry, they're labeled by this infinite degeneracy vacuum. And if you pick a very specific one, you break the symmetry. and it produces a ghost for you. The ghost is precisely the thing that's labeling the vacuum.
Okay, I see.
And so you can see all of these within the framework of the 2D CFDs we have.
Oh, thank you. I think this is very clear, and I'll certainly read your slides and watch your video some more, because this idea of deriving the boundary dual sounds really cool.
Thanks. It's mostly thanks to powerful machinery of algebraic geometry and twisted theory. Has to be this work.
Okay.
We have a lot of control over these methods.
Right.
Put that way.
Are there other questions from the audience? Anyone have any comments? If not, then let's thank Wei again. Thank you very much for giving this very clear and comprehensive talk.
Thank you, guys. There's still 7 people. Thank you, guys.
Yes.
Thank you.
Thank you very much. Yes, if anyone wants to contact Wei, just let me know. Or anyone wants his slides, just let me know. I can wait. So I will share your slides if someone asks for it.
Thank you. Yeah, no problem.
Okay, and if we have other questions, we can bug him later, privately. Thanks a lot. Okay, cool. Then I'll end it now.